Let's suppose that we have some discrete random variable x, and for the sake of simplicity, we're just going to let that be good old-fashioned roll of the dice. As we know, we can just express this random variable by its distribution. In this case, we can express it by its probability mass function, which is just going to be p subscript x of x. And this takes two possible values. Either it takes a value of 1 on 6, in the case that x is one of the possible face values of the die, so 1, 2, all the way up to 6, or if it's not a possible face value of the die, the probability of getting that value is just going to be 0. Alright, and so our question for this tutorial is, what is the expected value? What is the expected value of a random variable such as this, x? We represent that by a capital E with sort of a double struct left-hand side, square brackets, and the random variable x. Alright, and so immediately we can sort of give a bit of a loose interpretation to this as the long run average of this random variable. And what I mean by a long run average, I mean that if I kept sampling from this random variable, so I kept, rolling this dice and recording down the face value, and then I took all the face values for n rolls and looked at the average face value of that dice, then I let the number of dice rolls get very, very big, specifically get infinitely large, then what the average approaches, okay, the long run average, would be the expected value of this random variable x. Alright, so that's a useful interpretation, but it doesn't really help us computationally speaking. Okay, that's what we're going to aim to do next. So, for example, if we have some sort of sequence of rolls of this dice, they could be 1, 1, 2, 6, 5, 3, 4, 1, 3, 3, we have n rolls of this dice, okay? Then we know from this interpretation of probability as being the long run frequency, so we got a long run average, but probability is the long run frequency. Then we know if we've got a big enough n, if we've rolled this dice enough times, then 1/6 of all of those rolls are going to be 1s, and 1/6 of all of those rolls are going to be 2s, and so on, until 1/6 of all of those rolls are going to be 6s. And so this is true with a long run frequency if n is very large, okay, which is what we're interested in since the expected value is the long run average, okay. But if we have some large n and 1/6 of all of those rolls are 1s, for example, then the specific number of 1s we're going to have is n divided by 6. Okay, so let's return to our old-fashioned definition of a sample mean. And we know that a sample mean is just going to be 1 divided by n, the number of samples, number of observations, multiplied by the sum of all of the observations, where these little xi's are particular draws from this random variable x. Okay. But as we've just covered, in this particular case where n is very, very large, okay, we know that n on 6 of these observations are going to be a 1. And so if we want the sum of all of these observations, we know we're going to get, okay, n on 6 1s. And we know we're also going to get n on 6 2s. And so we can add n divided by 6 times 2 to our sum. This is going to be true all the way up to 6. So we're going to have n on 6 6s. And all we've done here is we've just rewritten this expression. Okay, rewritten this sum here as sort of the number of observations times the particular observation. But you'll notice straight away here that we've got 1 divided by n out the front, and we've got a multiple of n in front of each term of this sum here. And so we can actually cancel those out, which will just leave us with 1 on 6 times 1, plus 1 on 6 times 2, all the way up to 1 on 6 times 6. Well, we can evaluate this. This is just 3.5. Okay. But let's look at what we sort of simplified this expression to. We've just got a bunch of probabilities, multiplied by possible values of our random variable x. 1, 2, 3, 4, 5, and 6. Okay? And that's all we needed to calculate this expected value. Because we know in the long run frequency of a particular value is going to be, its probability. And if we're taking the sample mean, if we're taking the mean of this very, very large sample, we have 1 on n out the front. But we also know that the number of draws of a particular value, so the number of ones we have, is going to depend on this total number of draws. It's going to be the total number of draws times the frequency of that particular value, which is 1 on 6. And so we're always going to have this case where this 1 on n cancels out with the number of draws, which depends on n, the total number of draws. Okay? We always get this situation where this simplifies to just the probability multiplied by the value plus another probability multiplied by the value. And so we can actually, finally, we've got a formula for this in the case of a discrete random variable, which is just going to be the sum over all the possible values that this can be of that value multiplied by its corresponding probability. Okay, so we're done. In this discrete case, we've defined a mathematical expression for this expected value, for this long run average. Okay. That's all well and good for a discrete random variable, but half of the random variables we work with aren't discrete. We can't define a sum like this for most of the random variables that we work with. Okay? And so let's consider a continuous random variable, y, and for simplicity's sake, let's let it be distributed uniformly between 0 and 1. Okay. And so we still want to define something quite similar to this expression here. So we want to try and find out the expected value of y. And intuitively, this still applies. We still know that the expected value of y is just going to be the long run average. And we can still have this interpretation where we just take a very, very large sample. We let n, the sample size, get infinitely large. And we just look at the sample average, the sample mean, of that very, very large sample. That interpretation still holds. But unlike this discrete variable, where we could represent, the relative frequency of a particular number by this probability mass function here, we can't do that with a continuous variable because the probability of any given number is going to be precisely 0 because it's a continuous random variable. However, we still have a way of summing up over all these values. So we can write out, y, just like we wrote out x here. And instead of a probability mass function, we're just going to use the probability density function, fy of y. And although this doesn't tell us the probability of getting a particular value, it measures the density of probability at a particular point, okay? And whilst we can't use a sum like this, because we don't have a countable number of possible y's, of values for y, we've got uncountably many, okay? Whilst we can't use this sum, we can use a different kind of sum, which is called a Riemann sum. But you'll know it better as just an integral. And so just like this summation notation sums over every possible value of x, so too does this Riemann sum or integral sum over every tiny possible value of a random variable y. Okay? And in this particular case, we know that fy of y is going to be 0 for every value that's less than 0 or greater than 1. Okay? And so we can rewrite the bounds of this integral as 0 and 1. And we can write y. And we know the density of this is just going to be 1 in between 0 and 1. So we can just leave that blank as is. Okay? And then we can just evaluate this interval. And this will give us y squared on 2, evaluated between 1 and 0, which is just going to be 1 on 2. And going back to this more intuitive definition, this long run average, this makes perfect sense. Because after all, each value in this interval is equally likely. So of course, the long run average is going to be just the midpoint of this interval. Okay, so we've got two possibilities here. We have a discrete random variable and a continuous random variable. In both of these cases, we think about the expected value of that random variable as being the long run average. The average we'd get if we conducted infinitely many of this random experiment or this random experiment. Okay? However, the way we go about calculating this value, this expected value, changes between discrete and continuous variables. In the case of a discrete variable, it's just the regular old sum of the values multiplied by their corresponding probabilities. But in the case of a continuous random variable, it's still some sum over every value multiplied by its corresponding probability density. But instead of using the standard sum, we're going to use a Riemann sum or an integral.